Exponential and logarithmic functions were the last ones we met in this course. And even though we actually implicitly used a lot of what we now know to be the transformation of functions to help us understand them when we first met them, we can still make our discussion of exponential and log functions just a little bit simpler. First of all, I'm going to say that the basic form of an exponential function is f of x equals b to the x, where b is greater than 1. Remember, we initially defined these to have a base either between 0 and 1 or greater than 1. But I'm going to claim that the base greater than 1 is the basic form. Why? Well, if we have a base less than 1, we can write that base as 1 over b for some b greater than 1. Just take the reciprocal of our existing base. And then 1 over b to the x is just b to the negative x, which is a horizontal reflection. And we know that that's true. The graph that we have, if we have a base smaller than 1, looks like that, reflected across the y-axis, and here's why. Our example function here is 2 to the x. You can see that when x is 0, y is 1. When x is 1, y is 2. Like all exponential functions, this has the domain all real numbers. And since we're working with the basic exponential function, not multiplied by anything, it has range 0 to infinity. The inverse of the exponential, we now know, is the log in the same base. And considering this graph, it's fairly straightforward to see that there is no symmetry here. Right? If we reflect it across the y-axis, we have different shapes. If we reflect it across the x-axis, we have a completely different range. This graph has no symmetry. It does have one horizontal asymptote at y equals 0. And when we go to graph a function like this, the key points that we'll use are x is 0, y is 1, and then x is 1, y is whatever our base is. Remember, when we were initially graphing exponentials, we took the points where x is positive 1 and also where x is negative 1. We've restricted ourselves to the base being greater than 1. If we have a base less than 1, we'll use a reflection to fix that. So now we only need to look at those 2 points instead of needing to look at 3, which is neat. We'll make a similar move with the logarithms, so that our basic form will again have a base greater than 1. And again, if we have a base that's less than 1, we'll use the change of base formula to find that that's the opposite of the log base b of x for some base greater than 1. Our example here is the log base 2 of x. Notice we have the point 1, 0 and 2, 1. The domain of a log function is the same as the range of an exponential. It's 0 to infinity. The range of a log function is the same as the domain of an exponential. That's all real numbers. The inverse of a log function takes us back to an exponential. Like the exponential, the log has no symmetry and one asymptote. Now it's vertical at x equals 0. When we go to graph a log function, we use 1, 0 and b1, where b is the base again, which you'll notice is the result of swapping the x and y coordinates of the key points that we used for the exponential function. Not a coincidence. This is the inverse of the exponential function. Now, We can write everything in terms of bases that are greater than 1, which means that a lot of what we said about this happens one way, this happens another way, can be done away with. In fact, we can do even better. We can write everything in terms of the log base e. If we have a log in any base, we can use the change of base formula to say that the log base b of x is the natural log of x divided by the natural log of b. But this is a vertical scale with a factor of 1 over natural log of b. If we have an exponential in any base, we can mess around with the algebra a little bit and find that that's actually e to the natural log of b times x. We did that sort of change of base algebra several times when we were working with exponentials, although we didn't make it explicit in terms of variables. This is a horizontal scale, again with a factor 1 over ln b. Now, this isn't really useful to us in graphing, because the points that we actually get out of this all have e's in them, and actually plotting the number e is not fun. But it will be very useful in calculus, where you learn the meaning of the natural in natural log.